All right, so today's topic is the nuclear shell model. So in the last few lectures, we have been using deuteron as an example to explain how do we understand nuclear physics. So the role of deuteron in nuclear physics is just like hydrogen in atomic physics. In the case of deuteron, we have a neutron and a proton. In the case of hydrogen, we have electron proton. The interaction between them are very different. For hydrogen, protons and electrons attractive with each other through the Coulomb interaction. So the force is inverse proportional to R squared, or the potential is inverse proportional to R, which is proton 1 over R. And for deuteron, the interaction is approximated by the square wave potential. In fact, that is a very good approximation. So either way, so in quantum mechanics, how do we understand the atomic world in quantum mechanics? So we need an input, we need a VLFR as the input. Let me write them down. So in general, in quantum mechanics, what do we need? The input is VLFR. So the most important input is the VLFR. And given the interest potential, then by solving the Schrodinger equation, what do we get? Okay, the wave function, psi as a function of R. So in general, this wave function is a time dependent. But when we use separate variables, it's a VLFR does not really depend on time. So the time dependent part can be easily separated out. So usually we only solve the time independent Schrodinger equation, which will give us this small psi as a function of R. Okay. Then to get the time dependent part, we combine the initial conditions. So at time 0, what is the wave function? Then we're able to write down the total wave function as a function of time. Okay. And this wave function psi needs to satisfy a list of properties. For example, they needs to be continuous, and the first order derivative of the wave function needs to be continuous. In other words, the wave function needs to be smooth at the boundary, except at the infinite potential. Then the wave function needs to be normalized. If you integrate the wave function square from -infinity to infinity, we need to get 1 because the psi square represents the probability. So this is the general way to solve a quantum mechanics problem. So overall, the key point is the input is the interaction potential or the force. No, we don't directly use the force, we use the potential. This is actually it's the same as the other branches of physics. In case of classical mechanics, if we want to know the motions of a certain object, what input do we need? Same thing, we need to know the interaction. So, and even going beyond a single particle or single object mechanics, if you want to know the collective behavior of many, many units, for instance, if you want to know the phase behavior of materials or the phase, like I say, ideal gas, that's the simplest material, then we still need to know the interaction. So given in statistical mechanics, the input is also the interaction potential. If you know the interaction potential, and then when we plus the kinetic energy part is p squared over 2m, you get the total Hamiltonian. So, so oftentimes we say the input is Hamiltonian or the input is potential, so these two are equivalent. In the case of quantum mechanics, this step, solving the psi r from the VLFR, it's exactly like solving the eigenequation of the Hamiltonian. So if we know we know the Hamiltonian. So the H psi, H is operator, psi is equal to E psi. Okay. So this is the procedure to solve quantum mechanics. And then there are all kinds of internet potentials. One of the most important one actually is indeed the Coulomb potential. But in this semester, we are going to skip it. We'll come back to solve the Coulomb potential actually from almost the very beginning of next semester. So because potential itself is one of R, it's not like a square or stepwise potential. To solve that mathematically is actually quite challenging. And it's not, the result is not really concerned about nuclear physics. It's not directly related to interaction, for example, of neutron with matter. So that's why we're skipping that for now. So we'll come back to solve this 1R potential. So in this semester, if you think about what kind of potential have we solved, in fact, we have only dealt with two potentials. So the first one is an infinite square wave potential. So that is the example we use to explain quantum mechanics. So it's one-dimensional infinite square wave. So this is 1D potential. Okay, and the range can from anywhere from A to B. And in class, we use from 0 to A. And in homework assignment, then we put this range to be from -8/2 to +8/2. The solution is slightly different because the sine cosine function phase is shifted slightly. Okay, and in the midterm exam, I think it changed from -A to 0, which is actually very similar to from 0 to A. And then this one-dimensional potential has an infinitely high wall, so that no particle can escape outside the potential. And in the end, we only have the bound state solution. So only the bound state solution. If you consider this is like a particle, like a neutron, under influence of this internet potential, then there's no way for the neutron to escape from this potential, right? Because the wall is infinitely high. So there's really nothing outside the square wave. Then, but on the other hand, the structure of this solution is very similar to many of the more complicated solutions. When we solve this solution, we find the solution depends on quantum number n. So at the end of the day, there are multiple eigenstates. So not only one psi depend on n, and corresponding to each psi, we have the eigenenergy En. So we can draw like those energy levels. So there are multiple energies are allowed in this potential. Okay, then we quickly move down to a more released potential, which is indeed used to describe nuclear physics, and that is the three-dimensional square wave potential. Okay. As a function of R. So now, since it's 3D, it's a 3D potential, then we only plot the radial component. So the V of R doesn't depend on the theta and phi. So there's no angular dependence in the neutron-proton interaction. Okay, so from 0 to R, and then we say, so this interaction has a finite range. Okay, we call this range to be R0. And for neutron-proton interaction, this R0 is just the size of the deuteron, which is a 2.1 Fermi. So this is not. Now we didn't know the types of potential beforehand, but we know the bending energy of a deuteron. So the bending energy is indeed the energy needed if you want to remove the neutron from the proton. So if you pin the proton at the center, then this bending energies, indeed, it's just the energy, it's just the eigenenergy of the state of the neutron. So this is the energy level. And then we're also able to draw the wave function. The wave function turned out to have let me see, how do I draw that? It doesn't really matter, because in general we have to draw the wave function above zero. But in this case, we shifted the zero to be here so that we can still draw the wave function inside this square wave. So inside the square wave, the wave function is a sine function. The cosine function term goes away because of the requirement of normalization. Okay, and this wave function has a turnover inside the square wave, so that we have maximum probability to find out the neutron inside the deuteron. And outside the square wave, the wave function decays exponentially. Okay, but the probability is not zero. So know that the curve here I draw is the U of R, and the total solution will be the capital R of R, which is U of R divided by R. So this blue curve is the bound state solution. So unlike the above example, this one-dimensional square wave, which when we have a multiple eigenstates and multiple eigenvalues, in the case of deuteron, we only have one eigenstate, only have this psi 1 or psi 0, only one of the eigenstate. And this bound state solution applies to when the total energy is less than 0. Okay, total energy of neutron is less than 0. So if E is more than 0, then the solution is very different, because in that case, when we try to solve the Schrödinger equation, no matter whether the particle is inside the square wave or outside the square wave, we have the sine cosine function. Okay, and this type of solution is called the scattering state solution. Scattering state solution. So in general, when we have an interaction potential, unless the interaction potential goes to infinity, like the first case, one-dimensional potential, then we do have these two types of solution. One is the bound state solution, the other is a scattering state solution. Okay, of course, they describe this two distinct state. The bound state will be like in the neutron-proton system, will be when neutrons and protons band together and form a deuteron. And the scattering state solution describes when you see the solution is a sine cosine function. So they describe the plane wave, well, divided by our spherical wave. And they are the plane wave, I mean the wave that goes from minus infinity to infinity. So this propagating wave, and then, so that is indeed a scattering process. When send a neutron towards a proton, then how does the neutron get scattered? In classical physics, and we don't really need a wave function, then the scattering trajectory is determined. So that depends on how accurate you're aiming your target. But in quantum mechanics, this is very different. So the incoming particle is described by a wave, and the scattering is also described by the wave. And in the lecture I uploaded last week, you will see in the case of neutron-proton scattering, if the neutron comes in from very far away, then it is a plane wave. Right? And the scattered wave it's the spherical wave. And to compute the contribution to the scatter wave, we also need to approximate the incoming wave as a spherical wave. This is so-called S wave scattering. In general, we not only when you consider S wave, but also all the other waves, the P wave, D waves. But ice wave is really the leading term. In fact, oftentimes, most of the times, so only considering this term is already enough to describe the scattering process. So using that partial wave analysis and taking only the ice wave, and then we're able to find out how to express the differential cross-section, which is a central concept in nuclear physics. It describes the probability fail to detect the particle within unit solid angle. Okay, so that is the scattering state solution, and then we know this interaction potential from solving the bound state solution. Right? So the range is 2.5 Fermi, and because we're able to determine the spending energy, then we can inversely compute the depth of potential is minus V naught. Okay, so the minus V naught, then this V naught is a 35 MeV, okay, or minus 35 MeV. So compared to like Coulomb potential, in general, it's well, Coulomb potential is 1 over R. So there's really no bottom potential. It goes to like very, very deep. So, but this potential has a finite width, and this width, whether it's shallow or not, depends on what kind of unit we're talking about. If you see this is MeV, it's already very large energy. But this is a unit we use in nuclear physics. The 35 MeV in nuclear physics is actually pretty shallow potential. And that is why we only have one bound state for this neutron-proton system. For heavy nuclei, indeed, we can have like multiple red lines here. There could be multiple bound state. And that is used to describe the excited state of the nuclei. For deuteron, we don't have excited state. So it is a very shallow potential, and we only have one bound state solution. Okay. But this is so overall, this potential set up the foundations for us to move on to consider the more complicated nuclei. So with more than only one neutron and proton. So when we have multiple neutron protons bound together, then their interaction potential can still be approximated roughly by the square wave potential. Okay. So as I mentioned early in this section of the class is nuclear physics, we mentioned the nucleon interactions do not depend on the charge. The neutron-proton interaction is described by the square wave potential. Neutron-neutron interaction is actually the same. Okay. And furthermore, proton-proton nuclear interaction is also the same. Of course, in addition to the nuclear force, the strong nuclear force, proton-proton also repel each other through the Coulomb interaction. Okay. So for proton-proton interaction, we have both the nuclear term and also the nuclear force term and also the Coulomb term, so it makes it slightly more complicated. But overall, the shape of the interaction potential, even for heavier nuclei, can be almost the same as the square wave potential, except that now let's move on to a more realistic interaction potential for nuclear physics. Okay, so if we move on to more general nuclei interactions, let's draw from 0 to R. So the interactions can still be described by the square wave, except that this square itself is not a perfect square. So at the boundary, we don't have this sharp cutoff. So it becomes quite smooth. So it's roughly smoothed. Okay. And this is because in previous, as we mentioned, we have a we have a layer layer of layer inside the nucleus, right? The skin layer. So in this layer, the potential suddenly drops, but not as a step function, a smooth function. And then near the center of the nucleus, this interaction potential is almost a constant. Near the center, this potential is almost a constant. Draw better way. Okay. So this potential has approximated analytic form. So V of R will be equal to minus V naught, okay, which is still the depth potential minus V naught. And then over 1 plus an exponentially term. So R minus R divided by A. So this describes the skin layer. So when R goes to infinity, this exponential term goes to infinity, and then V of R goes to 0. So the shape of the skin layer is described by these two parameters R and A. So R is roughly the size of the radius of this nuclei. Okay, and typical parameters we use so for A it's a 0.524 Fermi, and so R, what is R? R is the 1.25, and the proportion, the cubic root of A, the atomic number, not atomic mass number, the number of neutron protons added together. And then the V naught is roughly 50 MeV. Okay. So this could be a potential. We can use to approximate heavier nuclei. And as you can imagine, if we plug this V of R into the Schrodinger equation, it's going to be more complicated. It's a bit more difficult to solve because now this V of R depends on R. In our previous case, roughly the V of R doesn't depend on R. It's just a constant in certain range. So we can solve the Schrodinger equations in different pieces. But now this V of R depends on R, just like a Coulomb potential. Then the solution is much more complicated. Okay, so in addition to this, there are a few other effects we need to consider. So one is the spin. So in the figure I draw above here is neutron-proton interaction. Got to do this. So neutron-proton interaction. We use this 35 MeV potential to solve the scattering problem, and then realize that the total cross-section actually not the same as the experimentally measured value. And the reason is this potential came from the bound-state solution of a deuteron. It only described the so-called triplet state, when the neutron spin and the proton spin are parallel with each other, roughly. When they are anti-parallel, the interaction is different. So this interaction of the nucleons is a spin dependent. Okay, so we need to add in the spin dependent dependence into this interaction. And spin, what is spin? So spin is the intrinsic angular momentum carried by those fundamental particles, neutrons and protons. Both of them have a spin described by spin quantum number 1/2. Okay, and in addition to the spin angular momentum, both neutrons and protons also have the so-called orbit angular momentum. So this orbit angular momentum roughly to describe the rotations of those particles around the center in the classical sense, but that's not exactly true. That is still a classical way of thinking about the angular momentum. But quantum mechanics, the particles do not really just go around. They are described by the state. So those are the additional details of quantum mechanics we're going to cover in 447. But for now, you need to know these interactions are spin dependent. Okay, so it's slightly more complicated than its interact potential. But at any rate, forget about all the details. So remember the procedure how we solve the quantum mechanics. If we have this interaction potential, then plug in the Schrodinger equation, then we're able to find out the eigenstate and corresponding eigenvalue. So indeed, the solution of this type of potential is described by this set of discrete energy lines. Like for each of them, we have the corresponding psi n and En. Okay. Of course, these psi n are not simply sine cosine functions. They are actually quite complicated functions. And we have the En. So not only the state depend on the n, they actually also depend on other quantum numbers related to the spin and the orbital degree freedoms. So the quantum numbers depend on n, l, m, like as the spin, a few other quantum numbers. Okay, but the important thing is that discretized. And then when we have neutrons, when we have more neutron protons, when we consider heavier and heavier nuclei, the neutron protons come in by feeding those right lines, starting from the lowest energy state. For each state, we can have for each of the quantum number, for each n, we can have multiple L. But for the different L, we can have a different M, which is the Z component of L, and we can have two spin state. So, and those numbers, those quantum numbers, N, L, M, S, etc., will determine the stability of the nuclei. So one level, one is right, one by level, I mean this right line, this right state, it's completely filled. Then the nuclei are more stable than the others. Just like in the case of the atomic physics, we have a different level of orbitals for the electrons. The electrons come in and fill in those electronic orbitals. Now, when every orbital is completely filled, then we have a more stable atom in terms of chemical reactivity. So for instance, all the inner gas, helium, argon, etc., have completely filled the electronic orbitals. So the electrons, there's no extra electron, also called valent electron, for them to react with other elements. So what they are called inert gas or inert element. So in the case of nuclear physics, we also have a set of these magic numbers, nuclear magic numbers. Okay, so these magic numbers are actually very similar to the atomic magic numbers. So like the first one is 2. You only consider the ground state. When we fill in 2 nucleons, then they become stable. So like we have 2, so here 2, now we have both neutrons and protons. So if we fill in 2 neutrons and 2 protons, that give us the maximum stability. That's why helium is also very stable in terms of atomic physics. So helium is actually this rare case. It's both stable in terms of chemical reactivity, but also stable in terms of the nuclear structure. Okay, so we have this 2, 8, 20, let's write down all of them, 28, 50, 82, 126. So these are the set of magic numbers which give us the most stable nuclei. Okay, so this set of magic numbers are not the same with the atomic physics because of the interactions are slightly different. When we go to higher energy level, is psi n or En, and also because of the coupling between the spin and the orbit, then this energy line, each of the En will split based on the other quantum number L and M, and overlap with each other, resulting in a different set of magic numbers. Okay. But on the other hand, physics here is not much than like atomic physics. Okay. And one more thing. So like in atomic physics, we talk about the valence electron. It's the actual electron, which is beyond this magic number. Then in nuclear physics, we can also talk about the valence nucleon. Okay, so for instance, if we have if we take a helium as an example, helium-4, we have 2 protons and 2 neutrons, and that matches the magic number, gives us the most stable nuclei or isotope for helium. But let's say if we remove 1 neutron, okay, that doesn't change its chemical properties much, almost nothing. If we remove 1 neutron, we get helium-3. I actually write it down here. So helium-4 and helium-3. So in the case of helium-3, what is the valence electron? In this case, we're missing 1. Right? We're missing 1 neutron. So, and that the valence nucleon, it's used to determine the nuclear properties. So this valence nucleon is basically determines all the nuclear properties. Okay, such as the spin of this nucleus, and the parity, the dipole moment, etc. It's basically the nuclear reactivity. And so again, this is very similar to atomic physics. When we have helium, helium is completely, in the case of helium, when the electrons are completely filled, we only have 2 electrons compared to lithium. The lithium have 3 electrons, and the actual electron is called the valence electron. So this actual electron is free to lose for lithium. That's why lithium has a very high chemical reactivity. Okay. So very similar here. And then we can also use these different labels to talk about the excited state. So in atomic physics, the excited state refers to when we move 1 electron from low energy state to the high energy state, and the atom excited. So the atom can lose energy by moving the electron back to the state it should be, and then the energy is released in the form of light, photons, and that light, because of the energy for the energy difference in atomic physics, is roughly in the order of electron volts. So that light can fall into the IR range, sometimes even the visible light range. And in atomic physics, in nuclear physics, we also have these multiple energy levels. We can also excite the energies of that particular nucleus. But the energy unit we have here is not electron volts, it's MeV. So when this nucleus de-excite, go to the lower energy state, the amount of energy that is released in the form of photon also has this unit of MeV. So that falls into like the X-ray and gamma ray, mainly in the gamma ray range. Okay, so the separation of gamma ray and X-ray is around 1 MeV, actually slightly less than 1 MeV, but roughly MeV. So if this difference in the En is a few MeV, then the energy that gets released is in the form of gamma ray. Okay, and this is the process of so-called radioactive decay. So this excited state can also be used to describe like a nuclear reaction. When we send in, let's say we're sending a neutron towards a uranium, and they forms a transient excited state. So the lifetime of the excited state is very, very short, and then very rapidly it decays and forms like multiple fission products. Okay, so all of them are essentially described by this model. And this model, because of, we have multiple levels, and this is what we call the nuclear shell model. So multiple layers, going back to the title for this lecture. Of course, there are a lot more physics and detail that go into this nuclear shell model. And of course, at this level, we don't really need to get into the details. But even if we go to higher level, we have to say this is a quite nasty subject, because of there are so many effects we need to consider, like the spin dependent and the spin orbital coupling. So there are indeed a lot of details. Okay. So one last thing I want to mention is related to the dynamics. The dynamics of the nuclei. So nucleus, because of the model we're using, so like say the liquid drop model, then we can also use that to describe the nuclear vibrations and nuclear rotations, like those collective degree freedoms inside the nucleus. It's not just a static droplet. The droplet can also vibrate and rotate. And these are phenomena that also observed in nuclear physics. Indeed, we can find out the nuclear vibrational frequency or vibration energy, or nuclear rotation degree freedoms. So again, there are more detailed properties of the nucleus, which can be explained by the nuclear model. Okay. So by that, I think we're gonna just conclude this short, very brief description of the nuclear shell model. In a nutshell, you can consider this nuclear shell model. It's just similar to the atomic shell model, except that the interaction is very different. It's much deeper. So the energy levels, the difference between different energy levels is much higher. We are changing from visible light to X-ray range to gamma ray range. Okay, but otherwise, in the structure, it's very similar to atomic physics. In atomic physics, actually, we can do these calculations much more rigorously, because the potential is simpler. It's 1 over. It's more complicated than the potentials we have solved in this class, but still manageable. And that is what we're going to do next semester. But on the other hand, the structures of the solution of nuclear physics and atomic physics are very similar. And the key result is this set of magic numbers. So in atomic physics, we have different set of magic numbers. Many of the numbers here are the same, but when we go to those larger numbers, because of the split of energies, they have a different kind of so-called degeneracies, different energies corresponding to the same n. Then we end up with a slightly different magic numbers. Okay, so that be the end of it's a second chapter of this class, the applied nuclear physics. The first part is introductory quantum mechanics. And moving forward from next lecture, so we are going to talk about the real interactions of radiation with matter. So we'll talk about three kinds of radiations: the neutron, charged particle, and photon. I think we'll go with neutron first, because now we're just able to find out the interaction potential and also the scattering cross section, and we use them to describe how neutrons interact with matter. And then we talk about the photon scattering, photon interaction, not scattering, how photon interact with matter, and lastly, how charged particle interact with matter. Okay, that'll be all for today.
Thank you.